Remember, we have to identify the domain. That's the first step. So normally I have to go through domain, table, graph, and number 4, range. Okay, so can anyone give us those intervals?
The first one would be open parentheses, negative infinity to -1.
Awesome. Second one. Perfect.
Open parentheses, -1 to
Very good. Excellent. And this one?
Is the closed 2 to infinity.
Excellent. So then let's establish the domain for this function. Awesome. Well done. Thank you.
Negative infinity to infinity.
Careful.
Negative infinity to -1, and then union -1 to 2, and then union.
Wait. 2 is not here, but 2 is here. But -1 is not in either one of them. So I'm not going to write it a 2 union 2 because it's the same point.
Yeah.
Okay.
That makes sense.
Perfect. Awesome. So number 2, we'll continue with the table. So of course in the table I have to have for sure several ordered pairs or several x values for which I determine the y value, but what are the x values that I need to have in the table for sure?
-1 and 2.
Very good. Awesome.
And negative infinity.
Excellent. So between negative infinity and -1, I know it's an overkill, but it establishes what we're trying to do. Which function do I use? Of course. So in between -1 and 2, of course, it's very clear, x squared minus 1, and from 2 to infinity, I have x plus 2. And now the symbols. To the left parenthesis, to the right parenthesis. Left parenthesis, right parenthesis, they cannot touch. This does not exist. They touch, for example, for 2, because we have a parenthesis and then a bracket. They have to touch. But if they are both parentheses, they cannot touch. Okay. Good, so let's plug in some numbers, something easy to calculate. This is not easy. When I plug in -1 and I have to, what do I get?
Square root of 2.
Very good. Not easy to plot. And give me a number that when I plug it in, it has to be between negative infinity and -1. When I plug it in, I can take the square root easily. Very good, awesome. So that's 4, so the square root of 4 is 2. Great job. On this side, what do I get? Very good, indeed. For 0, I get -1. What about for 2? Very good. What about for 2 here? Inside the bracket. And let's also look at 3. What do we get?
5.
Excellent. Any questions so far? Is this function continuous at 2?
No.
No. What is the limit from the right of 2?
4.
Perfect. From the left of 2?
3.
And from either side of 2?
Indeterminate.
Does not exist. Indeterminate is one of those 7 cases. And we encountered 3 out of 7 so far. Perfect. Okay, remember I will use 3 different colors, not to torture you, but to remind you that if I see something like this, I cannot give any credit for that problem. And I showed you a couple of examples. There was more than one student who did that. So I'm using 3 colors just to remind you that they will never overlap. Okay, so I'm using brown, red, and blue. Okay, first, okay, -3, 2. -1, the square root of 2 is difficult because this is approximately 1.41. So I'm going to graph it here, and it has plotted here, but it has to be an open point. If you draw this as a straight line, that will be incorrect. Remember how the square root function looks like. So the square root looks like this. It's not a straight line. It can be this way, it can be this way, depending on the function. So in this case, this function goes this way. Do not graph it as a straight line. It's not. Okay, I'm finished with this, and I will not continue to the right. This function to the right in brown. So now red, -1, 0. Still an open point. 0, 1. I'm sorry, 0, -1. And 2, 3. And that's also an open point. Now I have to remember how to graph this function, because the x squared function, when we talked about it, looks like this. But it's brought down 1, so it will look like this. But I can only plot what I'm allowed to, or I can only graph what I'm allowed to. This is what I'm allowed to. And I should have put also 1 here because it's 0, and that's important. So right here. Do not graph it as a straight line. It's not a straight line. Ah, I see what I did. That's why it was weird. It made no sense. So it's 2, 3. Okay. I went too far to do another point. So 2, 3. Done with red. Blue now. 2, 4. And this is a full point. And then 3, 5. Oh, here it is. 3, 5. And this is a straight line. Okay, 3 different colors. It's a function by the vertical line test. If I extend the red, or I extend the red this way, or I extend the brown, or I extend the blue, it will not be a function anymore. So this piece is brown, this piece is red, and this piece is blue. They do not overlap. Okay, so finally I want to determine the range. So the range is between negative and -1 to infinity. Remember, this is a square root function. This piece is a quadratic function. And this piece is linear. Always label the axis, etc., etc. So this is our f of x. So let's see if the problem is asking us to do anything else. Okay, yes, we're asked to present the definition of continuity at a point. Domain we have, the range we have, the table, yes, we have. Does the function have a removable discontinuity? Is it continuous from the left, from the right, etc.? Okay. So what will you say? Where is this function continuous? F continuous everywhere except where? Very good. Both, this one is undefined and jump, and this is jump. Is this function ever continuous from the left or from the right?
We say it's continuous from -infinity to -1.
Continuous from the left or from the right?
From the right.
Yes, Continuous from the right only at 2 because the function value and the limit are the same. So continuous from the right at x equals 2 only. Does this function have a removable discontinuity? No, it does not have a removable discontinuity. This is how a removable discontinuity looks like. The limit from the left equals the limit from the right, and it does not equal the function value at that point. So I will say no removable discontinuity. We are also asked to present the definition of continuity at a point. Limit as x approaches a from the left equals the limit as x approaches a from the right equals f of a. Remember, continuity at the point has 3 pieces. If you present only 2 pieces, you can't get full credit. Continuity at a point has 3 different conditions. Good. Anything else? Anything else you would like to go back to? Anything? 6, 7.
Can we go over the limit as x approaches infinity of arctangent e to the x?
Like this?
Yes.
Anything else? Or that's it?
That's it.
Okay, perfect. So, yes, every time we look at a limit or we are asked to calculate a limit, we have to plug it in and see what this is all about. So first of all, I have to start with the inner function. Let me write this. This is the starting point. This is the inner. And this is the last step. After I'm done with this, I replace x by whatever. I determine e to that. When I'm done and I get one number, then I apply arctangent to that number. So this is the outer. You can call this first and this second. Okay, so first let's look at the inner. As x approaches infinity, remember the graph and tell me where does this go? That's it. Good. Now, do you remember the graph of arctangent? We graphed it on the first day of classes. So here's the graph of arctangent. It has to be memorized. Okay, so this is y equals pi over 2, and this is y equals negative pi over 2, and this is arctangent. So now we know that this goes to infinity. So arctangent, when x approaches infinity, where does the arctangent go? That's it. So therefore the answer is pi over 2, which means that, of course, pi over 2 is a horizontal asymptote at infinity. Good. Next question.
Can you do an IVT?
Yes, yes.
You can do one from sample test number 6.
Okay, sure. So we have 2x cubed minus 8x squared minus 7 equals 0. Good. So IVT requires us to, number 1, identify the function. No problem. So this is our f of x. If I have something else here, I have to move it first, have 0 on one side, and then write the function. In step number 2, I have to write that f of x is continuous everywhere. I don't have to write this. I will write it because it's a polynomial, since it is a poly function. By definition, polynomials are continuous, defined, continuous, and differentiable everywhere. So now in step number 3, I have to plug the function in the graphing calculator. So go to y equals, clear if you have anything else in there, and plunge in the function 2x cubed, and then minus 8x squared, and then minus 7. Yeah, of course.
Doing the same thing as well.
Yeah, I saw that. 2x cubed. I did click here, but probably not forceful enough. I want 8x squared. And then minus 7. I'm going to check again just to make sure. 2x cubed minus 8x squared minus 7. Okay, and then I'm going to start plugging in numbers. Okay, I'm going to start with 0, and then move on to 1, and then move on to 2. Okay, I'll go back to -1. Okay, I will, we tried 0, 1, 2, -1. Let's go to -2. Let's go to -3. Let's go to -4. Okay, I'm going to go to 3. I'm going to go to 4. Okay, I'm going to go to 5. Got it. Between 4 and 5, the function changes sign. F of 4 is a negative number. F of 5 is a positive number. The function may have more than one solution. I don't care. I'm only asked to determine one. So since this, I have a function since it's continuous and it changes sign on the interval 4, 5, number 4 by IVT, I conclude and 1 through 3, there exists a C in the open interval 4, 5, open interval, such that f of C is 0. I don't have what the intercept is, but I guarantee you there is an intercept or a solution of the equation. That's the same thing. There is a solution of this equation or an x-intercept of this function, same thing, between 4 and 5, guaranteed by the intermediate value theorem, because the function is continuous and it changes sign.